button. Okay. All right, so solving exponential and log equations. We've seen a little bit of this already, right? We kind of looked at this last week where we happen to have some like commonality in the base, right? So if you have like a power of 3 and a power of 9, for example, we could sort of approach that by being, a little bit clever and rewriting and setting the exponents equal. We also talked about how you would do that with a logarithm, right? So ultimately, solving in a lot of cases comes down to, maybe doing some stuff to move things around and isolate the, quote unquote, like tricky part, the place where the thing we're solving for is, and then doing the opposite, right? Whether that's, I don't know, taking the square root of a square or, adding 1 where you were subtracting 1 or something like that to both sides. Here, for an exponential expression like this one, right? This is an equation that has an exponential term in it, and the thing I'm solving for is, sort of stuck up in the exponent, right? So that's what we mean when we talk about an exponential equation. Doing the opposite thing would be applying the inverse or the opposite to an exponential, which is a log. Yeah. So if I'm starting with an exponential thing, then at some point I'm probably going to end up taking a log or using a log. On the other hand, if I start with some kind of log term and I'm solving for a thing that's, stuck inside the log, I'm probably going to end up at some point rewriting or using an exponential to undo that. So just in case we need it as a reference, Jack, what's your favorite power of 2? 4. Okay, I like it. 2 to the 4th is 16. I actually do like that one because 2 to the 4th is 16 and 4 squared is also 16. So that's fun. How do you write that same thing as a log? The log base 2 of 16 is 4. Okay. So we're a week into now, I think, saying that being able to go back and forth between these things is, going to be important, relevant, and like this is finally kind of the big payoff for it. I want to solve 7 to the x equals 12 and find an exact value, right? Not just an approximation, get an exact value here. What can we do? Hey, what if we just rewrite it as a log, right? This thing is already the only thing on, that side of the equation. It's all by itself. So we have basically something that has kind of the same, shape, form, whatever you want to call it, as the exponential thing over there. Well, let's try just rewriting it as a log. The base is 7. Grady, give it to me one more time. Log base 7 of 12 is x. Oh, hey, what were we trying to do? Solve. Solve means find x as a number that makes the thing true. That's just some number, right? Like we did it. There it is, right? Jazz hands. The log base 7 of 12 is x, is the solution to the thing. Now, I might go check to see if that cleans up. If the log base 7 of 12 happens to be one that comes out nicely. I don't think it is. There you go, 1.27, some decimal junk thing, right? So, I didn't, luck out. It happens to be 6 and I just didn't recognize it or something. But because of that, I'm just going to leave it as it is and keep the exact version of it. There you go. Really, all we're doing is thinking of that as rewriting as a, I thought you were going over, man. I thought we're losing him. We're just rewriting as a log, right? I take the base, the exponent, and the other side, the answer, kind of switch places or switch jobs, and we end up with this. Okay. Now, another way that we can think through that's not really different, except for, again, maybe like how we're sort of conceptualizing it, is that I have this exponential thing that I need to eliminate, get rid of, undo. So the way to do that would be to use its inverse, right? Use its opposite, which is still a logarithm, but think about it as taking the log of both sides, right? Again, it's not really any different. But maybe feels a little bit more like what we're used to for, solving, right? I need to do something to this side. I've got 7 to the x. I need to get rid of the exponential thing and bring the power down. Okay, well, the opposite would be taking the log. Since I'm deciding to do it, right? This was my idea in the first place. I can decide what kind of log to use. Well, what might be a good choice? Like as a base. Yeah, 7. I mean, the base that you already have is 7. So let's try base 7. Base 7 is a good choice because what's the log base 7 of 7 to the x? If you want to get into it, you can take the power rule to bring that exponent down. And then what's the log base 7 of 7? 1. Right? How many 7s are in 7? Or what power of 7 is 7? Just 1. So the left-hand side just turns into x then, right? Whether you think of that as these things, sort of canceling directly, right, undoing each other and just leaving the exponent, or applying the power rule, and then this turns out to just be 1. We end up with just x on the right hand, the side that we've already done. Y'all know I can't do that. But we took the log of one side. That means we got to take the log of both sides. Now, again, I would probably grab my calculator and check the log base 7 to 12. It's some messy thing. I'm going to leave it like it is then. But we end up in exactly the same place, right? So if you're not comfortable or not as comfortable with the idea of sort of turning one of these into one of these, right? I always kind of think of that as like sort of anchoring on the base, and the whole thing kind of like pivots sort of. But if you're not as comfortable with that idea, then this is the same thing, right? It gets you to the same place, but it's a little more mechanical, maybe, like because you're doing the same thing to both sides, right? So it kind of automates it. Okay. We didn't have to use base 7. We are deciding to use a log to undo a thing that's already there, so I could use a different base if I wanted to. The important part, though, is that whatever you do on this side, you have to do the exact same thing on this side. So you can't apply, a log with a different base to the two different sides. They have to match. They have to be identical. Okay. Anybody have any questions about anything so far? Okay, so let's take a look at some of the practice problems that are here. Think about 5 to the x equals 13, which looks very similar. A good place to start with some of these is probably thinking about first, does it even make sense? What does 5 to the x look like? Like the function. Something like that, right? It's exponential, it grows. So something like this. We're asking where it's equal to 13. Well, 13 would be, somewhere up here. So it does at least make sense for those things to have an intersection, to have a solution, right? Sometimes it might not really make sense to be asking that. And if we're paying attention to what's going on, I might be able to tell kind of right off the bat, oh, hey, that's not going to go anywhere, right? There's not going to be a place where that's actually true. Normal solving stuff still applies where, this kind of ends up being the key thing that we need to do, but we might need to do some rearranging first. We might still have some work to do afterwards. If this had been 7 to the x plus 1, then I might still have some stuff to do, on the back end to finish solving, right? So let's take, 10-ish minutes or something, you guys, in 2s and 3s and stuff as usual. Give a couple of these a shot. Try a couple of the first two, but especially make sure you give a few minutes to try 4 and 5. Yeah. Yeah, so you just type in log and then there's a little, or if you just hit the underscore. Okay. Yeah. Yep. What? This is 6.4. 5. Yeah. Thanks, guys. Let's talk about 4 real quick. Yes, I assumed as much. Okay. That's the exponential part, right? That's where the thing that I'm solving for is. It's e to the 3x minus 2. It's not 5e all raised to a power. It's just, the e part is the only thing with the exponent on it. So what do we need to do first? I'm sorry, I didn't actually understand anything anybody said. Move the 1? Okay. Get that by itself first. So let me say isolate this first. Before we can do the log, we need to get the thing that I actually, the reason I actually want to do the log, get that part by itself first. So move the 1 over by subtracting, and then divide by 5. Okay, so really we're looking at e to the 3x minus 2 is 6/5. So I did. I had a whole existential crisis because you said you're a 3, and I'm looking here. I'm like, I don't think that's a 3. I do get confused sometimes. Okay, so now we've got e. Don't worry about what it is yet. So some power is 6/5. So what do we do? Take a log. What kind of log? The base is e, so let's use log base e or natural log, right? If I choose the log to match the base that's already there, that ought to make life about as straightforward as I can get it. So I'm going to take the log, the natural log, of both sides. Or rewrite it as a natural log if you feel comfortable with that. Either way is fine. What happens on the left-hand side is that we've got the natural log of a power of e. So we end up with just this, right? 3x minus 2. And on the right, well, I don't feel quite as confident about, estimating natural log. So natural log of 6/5. Okay. It's some messy jumbled decimal thing. I'm going to leave it like it is then, right? I want the exact value. I'm going to leave it as the ln of 6/5. That's just a number. It's just not a very nice one. The calculator's rounding it at 10 places or whatever, but I'm going to keep the natural log then. I'm doing this check to make sure that that doesn't just happen to be, exactly 2 or something that would be a little bit easier to work with. That's kind of the main difference in the stuff that we're looking at now versus the exponential equations that you've seen so far, like that came up last week, is that things aren't always going to come out quite as nicely here, but that's okay. I've got 3x minus 2 equal to some number, right? Again, don't get too freaked out about this. What do we need to do to solve for x? Isolate it, yeah. So add 2 and then divide by 3, right? That's it. Add 2. Okay. So I need to add 2. The only thing is that because the thing on the other side, the natural log term, is kind of messy and doesn't clean up nicely, I just have to leave it as it is. So I just write it as the log of 6/5 plus 2. And then divide by 3. So x is the log of 6/5 plus 2 all over 3, which again is not the prettiest thing in the world. But if you actually, once you get things copied down or whatever, if you step back a little bit and look at what we did a couple of like linear solving, just move stuff from one side to the other type of things, right? We subtracted 1, we divided by 5. We took a log to get rid of the exponential, right? Again, that's the key thing. Like if you have an exponential, you're almost certainly going to have to use a log to get rid of it. So we did that, right? Natural log because the base was e. And then, yeah, it's a little bit messy, but all we really did was add 2 and divide by 3. Right? We're just, again, pushing stuff over to the other side of the equation. Okay, questions about that one? Okay. All right, now let's take a look at 5. What's different here than the previous few? There's 2 of them, right? And there's 2 of them, and not only there's 2 of them, but there's 2 of those, right? That's the part that really messes with things. If this was 5 squared, that's not that big a deal because I can just say, well, I know what that is. And so we got variables on both sides. Well, not variables, they're unknown. Anyway, doesn't matter. The bases, right? That might be the next thing I'll look at. 2 on one side, 5 on the other. Well, 2 and 5 don't have anything in common, right? They're both prime. If they were 2 and 4 or something, then maybe I could, get away a little bit easier. But 2 and 5, there's nothing I can do to rewrite those to get them in terms of a common base to, find some like commonality there. So what are we kind of left with then? What can we do here? Any ideas? Okay, not that. We've got things that are in exponents that we need to solve for. We're going to have to do the opposite then, which is use a log, right? We're going to have to take logs, and we're going to have to just kind of, hit this thing head on. Like this is a place where we just got to brute force it a little bit. So I'm going to take the log of both sides. I'm taking the log of both sides, so I get to choose what kind of log, right? What do you think? What would be some good choices? 2 or 5, probably. I mean, we could use something like 10 just because my calculator's got a button for it, maybe like a neutral thing that doesn't really have anything to do with what's already here. But if I'm looking at this, I'm going to say, okay, well, I've got a base 2 on one side, I've got a base 5 on the other. I'm going to use one of those. I can't use them both because I have to do the same thing on both sides, but I'm going to use one. Any preference? Which? Okay, why 2? Okay, yes, no, I like that. 2 because the side with the 2 on it has the jacked up stuff in the exponent. Yeah, no, that's good. The base 2 side, that side of the equation looks worse, right? There's more going on there. Okay, well, why then do we choose that to be the thing we focus in on? Because when you take the log with that matching corresponding base, this happens, and we're just left with x plus 3 on the left-hand side. So choosing the base to match the kind of messier side means that it's going to clean up faster, right? The other side, well, not so much, right? It's the log base 2 of 5 to the x. What can we do with that? We can use the power rule to bring the exponent down. Let me actually write that a step before so I can just save us writing it again. Power rule lets me bring that exponent down. Now we're not done. We still have, more to do, but at least I've got the things I'm solving for out of the exponents now, right? So I took the log of this side. Since it's inside a log, I can take the exponent and bring it down using the power rule for logs. So I've got x times the log base 2 of 5. Okay. Now again, yeah. The thing you get to bring out is the power, right? And it's 5 raised to the x. Yeah, so that's the thing that comes down. Okay. Now, again, I might, pop off and grab my calculator and check real quick. The log base 2 of 5 is not pretty, right? Okay. Well, we're stuck with it then, but that's okay. We're solving. Here's an x. Here's another thing with an x in it, right? What do we need to do to solve? Pretend this part wasn't there. What would I need to do to solve? Get both the x's to one side and combine, get everything else to the other side. Okay, so let's do that. Three is x times the log base 2 of 5 minus another x. All right, now again, if this was just 5 and not the log base 2 of 5, then what would we do? I'd say, well, I got 5x. I don't want to take away an x, and 5 minus 1 is 4. So, okay, I've got 4 of them, and then I divide, right? Okay. I can't do that because it's not 5. It's whatever this is. So this and this don't combine as nicely as 5 and 1 would, right? I can't just like subtract and write down like, oh, it's 4. It's the difference in this thing and 1. So the way that we correct or adjust for that is to say, well, okay, I can't just combine the coefficients there. They're like terms, only I don't know a better way to write that log minus 1 than what it is. So the way we do that then is to say, well, there's an x here. How many x's? That many of them. This is some number, right? I don't know, 2 something, I guess. Minus 1 more x. Well, okay, again, I can't really combine those. I can't make that any nicer or more friendly looking than it is, but I can take this common factor of x and bring it out so that this is how many x's there are on the right-hand side. Again, this number is, messy and looks intimidating, but that's how many there are. How do we solve for x then? Don't worry about what that is. It's some number. Divide both sides by it, right? Divide both sides by this. They cancel there, which is good news. We get x is 3 over the log base 2 of 5 minus 1, which is a mouthful, but yeah.
On the like row with a couple highlights.
Yes.
Why wouldn't I just divide the log 2 by then? Why would I do it later?
Because if you divide by it here, you have to divide both sides, but you have to do it as both sides, not just individual pieces. So if you divide by this here, it would be 3 over the log. This part would just be x, but this would be x over that same log. Yeah. So it doesn't really change the problem. It just like moves when you would have to do it. Okay. Yeah. So ultimately you have to kind of get the x term sort of separated out first. These are, I mean, just to be, transparent, like these are tricky, right? Like there's a lot going on. This is probably of all the stuff that we do in this class, this is probably kind of the most dense thing, right? There's a lot going on here. Taking the log of both sides, right? That's how you get into it. And that's kind of the key thing. And the rest of it is just kind of working out the details, but the details are admittedly kind of messy. So I'm going to leave 6 for you to do. You can, look at my, try it first and then go look at solutions in Blackboard. But looking at this, what do you think would be a good way into it? Or how can we start that? Take the log base 7 because the side with 7 in it is worse than the other side.
So it's basically the same thing we did.
And it's going to look a lot like what we just did. But that's a, hearty shove in the right direction. Okay, so you do this one. And if we need to, talk about that on Thursday together, we can do that. Okay, let's take a look at on the back where instead of starting with an exponential, we're starting with a log and trying to solve. If we're starting with a log and trying to solve, then what do you think we're going to need to do? Like, how do you think this is going to go generally? Yeah, do the same thing, just go in the other direction, right? In the other order. So the way to get a thing out of a log or get rid of a log is going to be to use an exponential. So I'll circled the wrong thing there. So generally, like what we're going to be looking to do is get the log term, by itself first, if we can. That might involve just moving stuff from side to side, add, subtract, multiply, divide. That might involve using log properties, right? We can use those to, you tend to use those more to like combine or condense, but you can use those here as well. But then once I've got the thing to the point where I've got, a log term kind of all by itself, if I rewrite it as an exponential, then, things kind of clear up a little. So what could I do on something like 7 to get started? Okay. Can we do that right away? Okay. Isolate that first. So I need to move the 3 somehow. How can we move the 3? Divide, bring it back into the exponent using the power rule, right? Those are the 2 choices. Let's just try them. If I bring that 3 in, this would be the log of x cubed, right? Okay. Log, no base written, so it's a common log with, the like implied base 10, right? So how do I rewrite that then as an exponential? 10 to the 2 is x to the 3. 10 squared is 100. What would we still need to do to solve for x? Take the cube root. We're taking the cube root, so just be like thinking, root stuff. Cube roots are friendlier, right? If this was a square root or something, I'd need to be concerned or paying attention to picking up that like plus or minus term. It's a cube root, so we're good to go. So it's the cube root of 100. You can check that doesn't really clean up nicely, but that's what it is. Okay, and Ellie, you said divide by 3 first. Okay, let's see what dividing by 3 first looks like. So that's isolating the log term in a different way. So the log of x is 2/3. Now again, I've got the log term by itself, so let's rewrite it as an exponential. The base is still 10. So this would be 10 to the 2/3 is x. Hey, what's another way to write 10 to the 2/3? The cube root of 10 squared. Oh, that's the same thing as the cube root of 100, right? So those things are identical. They're not any different. Those are the same. So you could write this as the cube root of 100 if you want. To me, neither really cleans up nicely, so neither is really any better than the other. So we can use log properties to isolate that way and then do the exponentiating thing and then continue solving. Or if there's stuff that I could do kind of right away that's, quote unquote, like easy, right? Straightforward, like dividing by 3 here, then that maybe saves me some simplifying work on the back end, right? I did some more stuff at the beginning, then I rewrote it as an exponential and we were kind of done. Now, as usual, if it was the log of x plus 1 or something here, then I would just have a little bit of stuff to, finish with, right? If this had been x plus 1, I'd just move it over. So basically, like isolate somehow, then rewrite, and then if you still have stuff to move around to finish solving, then you go ahead and do that, right? So like number 8. Actually, you try number 8. You do this. I just noticed what time it is. How is something like 11 or 12 different?
So what I see right here, it shares both of it shares x and
There are 2 separate logs. They both have an x in them. I'm solving for it, right? So they both have the unknown inside that log. that means that, if we're talking about, the last one, and we kind of had some options for like how we get the log by itself, right? I could divide, or I could use log properties to pull that power in. Here, I can't isolate the log by just moving stuff around, right? By just pushing stuff from side to side. Because if I get this one by itself, then the other side's kind of a mess, and vice versa. So how else can we simplify, isolate, whatever, this to the point where I've got, the log of something equal to a number so that I can rewrite it as an exponential?
The X squared, something like that.
And I'll just highlight this plus sign in a suggestive sort of way. What can we do with the sum of two logs? You can combine them and multiply. So it's the log of x times x squared, or the log of x cubed. Right. We can combine those, condense those. Now I've got the log of something equal to 3. Again, it doesn't really matter yet what that is. What's the base? 10. Okay. So 10 to the base, that's the exponent, so 10 to the third is x to the third. If 10 cubed and x cubed are the same, x would have to be 10 then, right? Yeah. So LOG, log with no base, is common, so base 10. Yeah. So that's the one where the base is, implied. But yeah, that's base 10. Just as a, sort of by the way, here, you could also use the power rule if you wanted, right? You could take this 3, bring it down, divide it over, and end up at the same place, right? So there are some options here, and if you're kind of keeping, an open eye to that kind of stuff, you can apply these log properties. This is a place where, we kind of have to get started, right? Sum of two logs, I can combine those. Combining those lets me get to a place where I can use the exponential idea. Okay, now look at the very last two here, 13 and 14. What do you see? A problem. Yes. Okay, what's the problem? There are two separate exponential terms, and there's something else.
It's shaped like a quadratic.
But man, it's shaped like a quadratic, isn't it? I like that. Now you guys are on top of this thing, right? Like the first time we did this, everybody looked at me like I'm just from another planet. But e to the 2x minus ad to the x plus 15. If I wanted to, I could write that as e to the x squared. It's shaped just like a quadratic, only instead of being in terms of x, it's in terms of, well, orange blobby thing at the moment, or e to the x ultimately, right? So let's treat it like a quadratic with a is 1, b is -8, c is 15. So can we find things that multiply to 15 and add to -8? -5 and -3. If you didn't want to factor it, you could use quadratic formula, right? That's fine too. -3 and -5. Only difference is that it's quadratic in this thing, but now I've got it kind of broken up. It's in terms of e to the x. But the factoring part is the thing that lets us, kind of proceed, right? Like that's how we get into the problem. We use the structure, the quadratic, kind of structure form of the thing. correct. Except I can't write it. So e to the x is 3, or on the other hand, 5. And if it was just quadratic in terms of x, we'd be done. But since it's e to the x, we got one more thing to do. If e to the x is 3, forget about everything else that already happened. If e to the x is 3, then what's x? How do you solve this? Natural log. Yeah. X is the natural log of 3. And just because we did a bunch of, sort of mechanical, like algebra stuff, just to make sure that we're thinking about stuff, e to the x, we're asking where it's equal to 3. Okay, that makes sense, right? Or grab a calculator and check. Natural log of 3. Okay, 1 point something. I didn't get some kind of like error message or something about it being non-real or whatever. So that does actually make sense. That's one of our solutions. The other is x equals the log of 5. And similarly there, this has 2 solutions then. There they are. Okay. Everybody follow what I'm going for on that last little bit. Just because we kind of went into like just algebra, symbol pushing mode. And sometimes when we do that, we forget about thinking about whether things make sense. These are both perfectly valid solutions, so they're both good. If I'd gotten, -3 and 5, I would toss out the -1 because exponentials can't be negative. Okay, so there are a couple more there that we didn't get to. Try those and then use my solutions to check. Once you're done, if you have questions, let me know. 6.3 and 6.5 homework, you should pretty much be good to go. Thursday, we're going to talk about some like modeling and application problems. But not really adding any more like techniques to what we know. So get in there and do what you can. And if there are things that you have questions about, keep track of those. And we will reconvene on Thursday. So y'all have a good day. I will see you then.